Alright, in this video I would like to talk about series or infinite series, define what a series is, and then talk about the convergence or divergence of an infinite series. So first I want to distinguish series from a sequence. So we could have a sequence that looks like this, right? So the sequence, if we, like A1 would equal 1 over 1, A2, 1 over 2, and so on. So our sequence would look like 1, 1/2, 1/3, 1/4, etc. I want to distinguish that from, we use this summation notation, n equals 1 to infinity of a sub n. So what we're going to do there, instead of just have a list of numbers, we're going to add them up. 1 plus 1/2 plus 1/3 plus 1/4, and so on. And we can just keep adding all the way to infinity. Even though infinity is not a number, just keep adding and adding and adding. Obviously, the limit of this sequence goes to 0. The open question is whether or not, when you add up all the terms of the sequence, that's going to be a finite number or not. One way to think about series and whether or not they converge is to look at what's called the sequence of partial sums. So if we sum just some of the terms, a partial sum, so not the whole sum. For example, I use S for the sequence of partial sums. That would just be A1, or in this case 1. And then S2 would be A1 plus A2, which is 1 plus 1/2, which is 3/2. And then S3, that's A1 plus A2 plus A3, that's 1 plus 1/2 plus 1/3, and that would turn out to be 11/6. So we can have a sequence then, right? So the first term of this partial sum is 1, and then we have 3/2, and then we have 11/6. If we were to add 1/4 to that, we would end up with 25/12, and so on. And so one way to think about whether or not the series converges is whether or not the sequence of partial sums converge, right? Because each of these represent adding another term of the sequence, right? So if the limit as n goes to infinity of the sequence of partial sums converges, then, I guess I should say, if then the infinite sum, n equals 1 to infinity, converges. Okay, then likewise, I guess we'll just move back up here. If this limit of partial sums diverges, then so does the infinite series. Okay, so let's look at an example. What if I look at this particular series, n equals 1 to infinity of 1 over 2 to the n? All right, so what is that going to look like? Well, n is 1, I have 1/2. When n is 2, I have 1/4, plus 1/8, plus 1/16, and so on. It goes on to infinity. So let's look at the sequence of partial sums. So the first one is just 1/2. The second is 1/2 plus 1/4. Whoops, plus 1/4. It equals 3/4. Getting ahead of myself there. S3, that's going to be, well, S2 plus the third term, right? Because it's 1/2 plus 1/4 plus 1/8, or 3/4 plus 1/8. That's 7/8. If we were to add 1/16 to that, we would end up with 15/16. All right, so notice, if we want to go out and look at Sn, Notice 1/2, 3/4, 7/8, 5/16. One way to describe what's going on there is it's 1 minus 1 over 2 to the n, right? So 1 minus 1/2, 1 minus 1/4, 1 minus 1/8, 1 minus 1/16, and so on. So we can look at this. What's the limit as n goes to infinity of 1 minus 1 over 2 to the n? Well, that clearly is going to go to 0 as n goes to infinity. So the limit of the sequence of partial sums is 1. That tells us that this infinite series converges to 1. All right, and actually this series has a special property that basically the way that we get from one term to the next is to multiply by 1/2. And so if you have a constant ratio between terms, in other words, if you can get from one term to the next by multiplying by the same number again and again and again, that's called a geometric series. And that has some very nice properties. So let's define a geometric series and then talk about what those properties are. All right, so a geometric series is something of the form a times r to the n, and we're going from 0 to infinity. So by including 0, then when n equals 0, I'm just left with a, and then plus a times r plus a times r squared, and we just keep going forever. All right. So a is like the first term of the sequence, and then r is that constant ratio that we multiply to get from one term to another. So, for example, a could equal 2 and r could equal 1/3. And so what this would look like is the first term would be 2, and then we would multiply by 1/3 to get 2/3, and then multiply by 1/3 to get 2/9, and then multiply by 1/3 to get 2/27, and so on. This is an example of a geometric series. So let's look at what the nth partial sum would look like. All right. So we're going to have a plus a times r plus a times r squared all the way out to a times r to the n minus 1. All right, and that's the nth term because we started with n equal to 0. So if we go to n minus 1, that's n terms of the nth partial sum. And here's a little trick we're going to do. We're going to multiply both sides of this equation by r. So what does that give me? Well, a times r is ar. Ar times r is ar squared, and so on, out to, we're going to have a r to the n minus 1, and then finally this last term turns into a times r to the n. And the reason for that is not exactly clear until I show you what we're going to do with it. What we're going to do is we're going to subtract this equation from this equation. We know we have two things that are equal. We can subtract basically r Sn from Sn. And the reason we're going to do the subtraction is it really simplifies what's going on over here, right? Because notice ar, this has an ar, this has an ar, this has an ar squared, this has an ar squared. This cancels, this cancels. All the terms in between cancel, so we're just left on this side with a plus a r to the n. All right. So here I'm going to factor out in my my Sn, which is my nth partial sum, and I'm left with 1 minus r. And on this side, I'm going to factor out an a, and I'm left with 1 plus, whoops, sorry, that should be a minus, shouldn't it? Because I subtracted all these. That's a minus, so 1 minus r to the n. All right, so to solve for the nth partial sum, I'll divide both sides by 1 over r, so I end up with a, and I have 1 minus r to the n over 1 minus r. So first, that's a convenient way to be able to write the nth partial sum. So for example, we could see here with this particular one, so a was 1, right? And then r was 1/2. Now the difference is this starts at 1, and this one starts at 0. But really, if you look at this, if n was 0, that would just add 1, right? Because 2 to the 0 is 1. So one way to think about the nth partial sum of this particular series here, if we use our formula, is it would actually be, well, let's just call it 1. We can always subtract 1 at the end because we know that this starts at 1/2 instead of 1. But it would be 1 minus 1/2 to the n over 1 minus 1/2. And we could simplify that to get this after we subtract 1 off. So it's a convenient way to get the nth partial sum. But more importantly, what happens if r in absolute value is less than 1, then what happens to the limit as n goes to infinity of my partial sum? Because this limit, we said, that is, if that converges, then so does this. All right? Well, this is the key. If my constant ratio is less than 1, so for example, in the previous case, it was 1/2. So you're multiplying by 1/2. The terms are always getting smaller and smaller and smaller and smaller. What happens here, right? Well, this is the one that we want to take a look at. What happens if r is less than 1? What happens to r to the n as n goes to infinity? Well, if you think about it, it goes to 0, right? Because you can have 1/2 times 1/2 times 1/2 times 1/2. It's going to get smaller and smaller and smaller and smaller and go to 0. So what we end up with is a times 1 over 1 minus r, which we can just write as a over 1 minus r. So this is actually really nice because we can take this whole infinite series and we know that it will converge to that. Now I should note that if r in absolute value is greater than or equal to 1, then the geometric series diverges. So it's only going to converge if we have that. So I know we're all just kind of we're working right now with just like a's and r's and stuff. So let's just look at an example. So if I have, for example, from the sum from n equals 0 to infinity of 3 to the n over 5 to the n. All right. I could rewrite that as 3 over 5 to the n. So what we're looking for here is, first, recognize, because we're basically multiplying, this 3/5 to the n means we're going to be multiplying by 3/5 over and over again for each term of the series. So that indicates that it's geometric. What would a be? Well, when I put in 0 for n, that's going to be 1. And then my ratio, the constant ratio multiplying by, is 3/5. So if I want to find, so first, because it's 3/5, because r is less than 1, we know this is going to converge. And it's going to converge to this, a over 1 minus r. So that's 1 over 1 minus 3/5. That's 1 over 2/5, which is equal to 5/2. So very convenient way. If we have a geometric series, it's really pretty straightforward to determine how, or if it converges and what it might converge to. If we were to flip this around, just say this real quick because I think it's obvious from what I said right here, but if we were to flip this around, so over 5 to the n over 3 to the n, well, that's 5/3 to the n. It's geometric. A would equal 1, again, because, well, we're starting at 1, and then we start at 1, we multiply by 5/3 to get the next term, we multiply by 5/3 to get the next term. These terms are getting larger and larger and larger, right? So with r equal to 5/3, which is greater than 1, we know that this series will diverge. So if we have a geometric series, it's pretty straightforward to determine if it converges or diverges, and if it converges, what it converges to. All right, just a little bit more about the divergence and convergence of series. A couple different, just a theorem, and then one other example of a series that is easy to determine if it diverges or converges. So the theorem says that if I have an infinite series that converges, then if I take the sequence, those terms of this, so again, just let's kind of come back and look at an example. So here, this is the series. We're adding the terms up. And what this theorem is saying is if this converges, then what can we say about the sequence? All right? And what we're saying is that the sequence would go to 0. All right? So the terms, in other words, the terms of the series have to get smaller and smaller and smaller, going all the way down to 0. Well, not if you have a series that converges, and that's what's going to happen with the sequence. Those terms will get smaller and smaller and smaller and go to 0. Now, this is really important. Okay, make a big exclamation point, not a factorial. That if the converse is not true, if the limit as n goes to infinity of a sub n equals 0, this is the temptation. This is what you're going to want to do. Is you're going to want to say, well, I just look at the sequence, and if the sequence goes to 0, then I know that that the infinite series converges. All right, that is false. All right, that is not true. And a counterexample actually is the one that we started with. If we look at n equals 1 to infinity of 1 over n. Now, we haven't shown this yet, but we will see later on that this series diverges. We will show it later. But for now, take my word for it. It diverges, but of course the limit as n goes to infinity of 1 over n equals 0. So it doesn't work the other direction. Now, that's the converse. That's just switching and saying if this, then this. And that's false. But the contrapositive is logically equivalent. So what is the contrapositive? It means if I negate this, then I negate that. So what does that mean? It means if the limit as n goes to infinity of a sub n is not equal to 0. In other words, if those terms of the sequence don't go to 0, then we know that the infinite series will diverge. All right. Okay, so let's maybe take a look at an example. All right, if we want to take a look at, what do we have? N equals 1 to infinity of n factorial over 2n factorial plus 1. And we want to determine just if it converges or diverges. So let's take a look at this sequence, right? If the sequence equals 0, if the sequence goes to 0 as n goes to infinity, then we don't know anything. It could converge, it could diverge. But if it doesn't go to 0, then we know that it diverges. So let's take a look at that. Limit as n goes to infinity of n factorial over 2n factorial plus 1. So we could just multiply top and bottom by 1 over n factorial. That will give me 1 over, so if I multiply through here, that becomes 2 plus 1 over n factorial. So as n goes to infinity, that's going to go to 1/2, which is not equal to 0, so this must diverge. Okay, one last type of series that I would like to discuss here is called a telescoping sum. This is another example of a convergent series, but we have to be able to recognize the pattern and sometimes kind of create the pattern. So let me give you an example to begin with. We have n equals 1 to infinity of 1 over n minus 1 over n plus 1. Now this is pretty straightforward. It's getting it into this form often that will take a little bit of work. But let's just starting with a simple example. This is going to be 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, and so on. All right. So it may or may not be obvious, but the nth partial sum will be 1 minus 1 over n plus 1. So I'm not going to worry right now about kind of showing that, but take my word for it. Now, if we take the limit as n goes to infinity, then clearly if we look at this is going to go to 0, so that's going to just leave me with 1. And remember, the limit of the limit of the sequence of partial sums gives me the sum of the infinite series. All right, so that's the sum of the infinite series is 1. Another way to see this is if we just drop all these parentheses, I end up with 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4, and so on. Right? So I'm going to cancel, cancel, cancel. Everything all the way out to infinity will cancel except for the first term. So that will equal 1. So let me just give you, like I said, in this case, it was very obvious, right? We have this minus this. When we write out the terms, it's very obvious that we have this, what's called the telescoping sum. It's called telescoping because it collapses in the same way that a telescope collapses with all this cancellation. So I just want to show one more example of a telescoping sum where it's not so obvious that what we have, at least initially, it's not obvious that we have a telescoping sum. So here's the example. So if you just look at it, it doesn't look like the one that we had previously here, where you're just taking one thing and you're subtracting something else. So the sum is going to be a sum of differences, and then you get this cancellation. Here, it's not so obvious that that's what's going on until we factor the denominator. Right, so this is going to be the same as 2, and this is a difference of squares, so I can rewrite that as 2n plus 1 times 2n minus 1. So now I have these two factors. That's the thing, when you have two things that are multiplied, what we could do is we could separate those out into something over 2n plus 1, and plus or minus, I'm just going to say plus, something over 2n minus 1. Ultimately, we want this to be a minus for the telescoping, but what that means is whatever the numerator here is, the numerator here will likely be negative. So it'll turn into a telescoping sum. So what we need to do at this point is figure out what should these numerators be, so that if I were to put this back together with a common denominator, I would end up with this. All right. So what I'm going to do is I'm just going to call this one A, and I'm going to call this one B. And in order to determine what A and B are, I'm going to go ahead and recombine these in terms of A and B in this manner. So we know that we'd have to multiply to get back to this denominator. I'd have to multiply the denominator here by 2n minus 1. So I do the same thing with the numerator, and I end up with A times 2n minus 1 over, well, the whole thing is going to be over 2n plus 1 times 2n minus 1, right? Oops, let's see, make that a little bit more. Okay, and then of course b gets multiplied by this, so I'm going to say plus b times 2n plus 1. So we see now that in order for these to be equal, since the denominators are equal, the way that these two things will be equal is if 2 equals, and let me just go ahead and distribute here, 2an minus a plus 2b n plus b. So these need to be equal in order. So I need to basically solve for a and b so that these are equal. Now notice that this is a coefficient of n, and so is this. So let's first combine those. That gives me 2a plus 2b. That's the coefficient of n, and then I have minus a plus b. So now let's compare these. Now again, I'm looking at a and b as constants here. All right. If they're not, but let's just take a look at this. There is no n term over here, so that means that the coefficient of n has to be 0. All right, and then these are my constant terms, and I know then that negative a plus b is going to equal 2. All right, so now I have two unknowns, two equations. I should be able to solve for a and b. Right here, if I divide both sides of the equation by 2, I end up with a plus b equals 0, or a equals negative b. And I'm going to take that, substitute it in here for a. So now I end up with what? Negative b plus b equals 2. So 2b equals 2, and b equals 1. All right. Then, if b equals 1, because of this relationship, we know that a equals negative 1. So if we go back to this, what I know is that the sum from n equals 1 to infinity of 2 over 4n squared minus 1 equals negative 1 over 2n plus 1 plus 1 over 2n minus 1. And again, for this to be a telescoping sum, I'd really like the negative to be on the back end. So let's just rewrite that as 1 over 2n minus 1 minus 1 over 2n plus 1. Because now we're going to see this is going to be a sum of these differences. Let's look at what those will look like. If I let n equal 1, I'm going to end up with 1 minus 1/3. Plus, now if I let n equal 2, I'll end up with 1/3 minus 1/5. When n equals 3, I end up with 1/5, right? 6 minus 1 is 5, 1/5 minus 1/7, and so on. So we see the telescoping nature here. Every term cancels except for the first, and so once again, it sums to 1. So this is the technique here. Sometimes you're going to get things, either they might be already factored, or maybe you'll have to factor it. But if you can factor it into two terms, and then rewrite those this way, get a common denominator, solve for a and b, and then ultimately rewrite your series as a telescoping sum, then it's an easy way to determine that it converges and what the limit is.